The purpose of Lab 1 was to find a real-life example of an object moving at constant velocity and compute its position versus time data using Newton's second law. Delta V over delta t equals F net over m, and then comparing the observed data to a prediction of that data done by a computational model. To do this, I observed a person walking at constant velocity along a straight line and used the initial data points from my observation to create a computational model to predict the position and time of the object's motion according to Newton's second law in the following forms. The final velocity equals the initial velocity plus the net force, which is the sum of all forces or pushes and pulls on an object, divided by that object's mass times the change in time. And, in another form, the final position equals the initial position plus the average velocity times delta t. My findings were that my observed data had a much higher velocity than the predicted data, but possible reasons for this error will be discussed momentarily. I observed a girl walking at constant velocity from the negative x direction towards the positive x direction. I extracted her position versus time data from Tracker and was then given the observation start time, object's initial position, time in the second frame, and object's position in the second frame. This data was used to calculate the average initial velocity by change in position over change in time, from t equals 0 seconds, which was the first frame in Tracker, to t equals 0.0335 seconds, the second frame in Tracker. Then, I constructed a computational model of what the object's path should have looked like according to the obtained first data points from Tracker and Newton's second law. The model implements Newton's second law to predict the velocity and position of the future. In order to do this, we have to assume that there are no net interactions from the surroundings. We do this in the code by setting F net equal to 0, initial position point, ball.pause, to the initial position point obtained in Tracker, and initial velocity point, ball.vel, to the average initial velocity calculated from the first two data points obtained in Tracker. And lastly, the mass of the object, ball.m, to the mass of the girl walking, approximately 57 kilograms. The code then calculates at 1/1000th of a second later the new velocity and position at each time step, which is why we use a loop in the code of Newton's second law in the form of final velocity equals initial velocity plus F net divided by mass times delta t, and final position equals initial position plus average velocity times delta t. If F net equals 0, then we can see in the code that the velocity is constant, because velocity equals velocity plus F net divided by mass times delta t. Also, velocity final equals velocity initial, so therefore constant, meaning that the mass has no effect on the prediction of velocity. And it also means that the size of delta t is relatively insignificant, which in this case is good for us, because Tracker measured delta t as 1/30th of a second, whereas the computational model measured each time step as 1/1000th of a second. Therefore, we could rewrite the equation as more simply v of t equals v naught, because velocity is constant. And r of t equals r naught plus v naught of t, because the position of the next time step is going to be the position of the time step beforehand plus the constant velocity. While the computational model from VPython gives us a pretty accurate image of the object's motion, in comparing the data observed from Tracker, the blue dotted line you see here, to the data compiled from the computational model, the solid red line, it's easily noticeable that while both sets of data indicate a relatively constant slope, meaning constant velocity, the velocity of the observed data is much higher than the velocity of the predicted data. The motion was constant and uninterrupted. However, there could be interactions by forces that have not been accounted for in the Tracker observation of data. For example, the object was walking along a court, but some of the motion exerted was used not only towards propelling the object forward, but with each step that she took was elevated off of the ground and then lowered slightly back down. This could have affected the object's average position in Tracker. If you flip back and forth, you can see the change in the y component. Also, the computational model is assuming that F net equals 0, when, in reality, the system can't have exactly zero net force. There is friction on the surface that the object is walking on, air resistance, and other minuscule and almost negligible forces that can still cause a discrepancy in the observed versus predicted data. In response to the what-if question, if the axes were flipped and the negative x direction became the positive x direction, and vice versa, the data would be in the same slope, just in the negative direction. Therefore, the slope would be downward. In response to the what does it mean question, it is not exactly known how many forces are on the object, because there could be amounts of wind resistance and other aspects of the surroundings that could have just been flighting. However, we know that gravitational force, normal force, and friction were all forces on the subject. In conclusion, in order to observe Newton's second law in cases of constant velocity, the net force should be equal to zero, thus causing the object's mass and change in time to be of little importance. The object I observed did not experience total zero net force, and due to its motion towards the positive y-axis, did not have the same constant velocity results as predicted by the computational model.